Moving on to Chapter 9, the distributed nervous system, interagent communication patterns. Now, let's explore theoretical foundations. The fundamental challenge of deploying intelligent systems is not the intelligence itself, but the logistics of delivering that intelligence reliably, scalably, and efficiently to the end user. We are moving from the era of monolithic scripts to distributed intelligence. This transition requires a rigorous theoretical foundation in how software components communicate, how state is managed, and how resources are allocated in a cloud-native environment. Now, let's talk about the analogy, the central kitchen versus the food truck fleet. To understand the architecture we are building, imagine a high-end restaurant, a monolithic AI application. It has one large kitchen, one menu, and if the dinner rush hits, the only way to serve more people is to build a bigger kitchen. It is slow to expand, expensive to maintain, and if the oven breaks, nobody eats. Now, imagine a central cloud kitchen, Kubernetes, that coordinates a fleet of specialized food trucks, microservices/containers. 1. The kitchen, Kubernetes. It doesn't cook. It provides the infrastructure, the gas lines, power, the water, networking, and the parking spots, scheduling. It monitors the trucks. 2. The food trucks, containerized agents. Each truck has a specific job. One makes just the burgers, text generation, one makes the fries, image recognition, and one handles the drinks, voice synthesis. They are self-contained, they have their own engine, their own ingredients, and their own kitchen. You can move them anywhere. 3. The menu, the agent interface. Even though the trucks are different, the menu is standardized. You order a meal, the request, and the kitchen orchestrates the trucks to deliver the components. 4. Scaling, auto-scaling. When the lunch rush hits, high traffic, the kitchen doesn't renovate. It simply calls more burger trucks to park in the lot. When the rush ends, it sends them away to save gas. This is the essence of cloud-native AI, decoupling the model's logic from the execution environment to allow for elastic scaling. Now, let's talk about the what containerizing AI agents. In the context of C# and modern .NET, an agent is not just a class, it is a self-contained unit of execution that perceives its environment, makes decisions based on an LLM, large language model, and acts via tools. Why containerization? AI models are heavy. They require specific versions of Python runtimes, CUDA drivers for GPUs, or specific ONNX runtime versions. If you install these directly on a server, you create dependency hell. If you update a driver for one app, you might break another. Containerization solves this by packaging the agent logic, C# code, the model inference engine, and the OS dependencies into a single immutable artifact, a Docker image. In C#, we leverage Dockerfile to define this environment. But theoretically, we must understand that the container is the atomic unit of deployment. It allows us to treat an AI model exactly like any other software component. Now, let's talk about the why microservices and the .NET host lifecycle. Why break a complex AI application into microservices? Consider a customer support agent. It needs to 1. Read the user's intent, NLP. 2. Check the user's account balance, database. 3. Generate a polite response, LLM. 4. Send an email, external API. If this is one monolithic process, a failure in the email API, step 4, might crash the whole process, losing the context of the NLP and the LLM generation. By using microservices, we isolate these concerns. The email service can fail, and the orchestrator can simply retry or notify the user, while the generation service remains unaffected. The role of iHost and background service in modern C#, we utilize the generic host, iHost, to manage the lifecycle of these agents. This is a concept heavily refined in .NET 6 and beyond. An AI agent is rarely a simple console app that starts, does one thing, and dies. It is a long-running service that must listen for incoming requests via HTTP, gRPC, or message queues. Manage memory efficiently, handling large model weights. Handle graceful shutdowns, saving state before the container is killed. The background service abstraction is crucial here. It allows us to run the inference loop inside a standard .NET host, which integrates seamlessly with container health checks and orchestration signals. Moving on to the how interfaces and dependency injection for model swapping. A critical architectural pattern in AI engineering is the strategy pattern, implemented via dependency injection, DI, and interfaces. This is where C# shines. AI is volatile. Today you might use OpenAI's GPT-4, tomorrow, cost pressures might force you to switch to a local open-source model like Llama 3, or perhaps a specialized model for code generation like DeepSeek Coder. If your business logic is tightly coupled to OpenAI client, you are trapped. The solution: we define the capability of generating text as an interface, not a concrete implementation. We begin by defining the core contract for our AI inference agents with the IInferenceEngine interface. Notice at line 5, this interface declares a single asynchronous method, generate async. This design choice is fundamental for several reasons. First, using an interface promotes loose coupling, allowing us to swap out different AI models or providers, like OpenAI or a local Llama model, without altering the client code. This is a cornerstone of microservices architecture, enabling flexibility and independent evolution of components. Second, the task string return type at line 6 signifies that inference operations are asynchronous. This is crucial for cloud-native applications, as AI model inference can be a long-running process. Performing it asynchronously prevents blocking the main thread, ensuring the application remains responsive and can handle multiple concurrent requests efficiently. This directly supports horizontal scalability, as the web server isn't tied up waiting for a single AI response. Following our interface definition, we see two concrete implementations, OpenEngine at line 10 and LocalLlamaEngine at line 12. These represent two distinct strategies for performing AI inference. The OpenEngine would typically encapsulate calls to a cloud-based API, like OpenAI's GPT models. This approach offloads the computational burden of inference to a managed service, simplifying deployment and scaling from our perspective. In contrast, LocalLlamaEngine implies running an AI model, like a Llama variant, directly within our application's container or on a local machine. This choice has significant implications for resource management. A local engine requires the container to provision sufficient CPU, GPU, and memory resources to host the model, which can be substantial. The decision between these two implementations often hinges on factors like cost, latency requirements, data privacy, and the specific hardware available in the deployment environment. The beauty of the IInferenceEngine interface is that our application logic doesn't need to know which concrete implementation it's using, allowing for runtime configuration and A/B testing of different AI backends. By injecting IInferenceEngine into our agent's constructor, we decouple the agent's reasoning from the model provider. This allows us to deploy the same container image to different environments, dev versus prod, and simply change the configuration to swap the underlying engine. Moving on to orchestrating multi-agent systems. When we scale to complex inference, we rarely use one agent. We use a swarm. This introduces the concept of orchestration versus choreography. Choreography: each agent acts independently based on events, like dancers in a flash mob who have no conductor. Orchestration: a central entity, the orchestrator, directs the agents. In our C# architecture, we often use a pattern similar to the mediator pattern, via libraries like mediator, or a custom orchestrator class. The orchestrator holds a list of registered iAgent instances. The flow: 1. The orchestrator receives a complex task, analyze this financial report. 2. It decomposes the task. 3. It dispatches subtasks to specific agents: data extractor agent, high CPU, short duration. Sentiment analysis agent, high memory, long duration. Summarization agent, lightweight, fast. The theoretical foundation here is asynchronous message passing. The orchestrator does not block. It sends a command and awaits a response event. This is vital for scaling. If the sentiment analysis agent is slow, it doesn't block the data extractor agent from processing its part. Turning our attention to scaling inference, the economics of latency and throughput. This is the most complex part of the theoretical foundation. In standard web apps, scaling is about throughput, requests per second. In AI, we must balance throughput with latency, time to first token, and cost, GPU time. The GPU bottleneck: GPUs are expensive. Unlike CPU cycles, which are cheap and plentiful, GPU cycles are gold. You cannot simply spawn more GPUs instantly. Strategies for scaling: 1. Horizontal pod autoscaling, HPA. This is the standard Kubernetes approach. We monitor metrics like CPU/memory usage or, more specifically, queue depth, how many requests are waiting for the GPU. If the queue grows, Kubernetes adds more pods, replicas of our container. Constraint: this requires the model to be loaded into memory for each replica. If your model is 50 GB, you can only fit a few replicas on a node. 2. Model sharding, tensor parallelism. For massive models, like GPT-4 scale, a single GPU cannot hold the model. We split the model across multiple GPUs within a single pod. In C#, we manage this via the underlying runtime, like ONNX runtime or Torch Sharp, configuring the execution provider to utilize multiple CUDA devices. 3. Batching. Instead of processing one request at a time, the inference engine waits a few milliseconds to collect a batch of requests and processes them simultaneously. This drastically improves throughput, requests per second, but increases latency, the wait time to form the batch. C# implementation, we use channel T or data flow blocks to buffer requests and flush them to the model at fixed intervals. Moving on to observability, the nervous system of the swarm. In a distributed system, it works is not enough. We need to know how it works. Distributed tracing, OpenTelemetry. When a user prompt travels through the orchestrator-sentiment agent-inference-engine-database, we need to see that journey. In C#, we use activity source and activity classes to instrument our code. This allows us to visualize the request flow and identify bottlenecks. Metrics, we must expose metrics for the scraping engine, Prometheus. Inference_duration_seconds, how long the model took to generate. Tokens_processed_total, for cost analysis. GPU_memory_usage, to detect memory leaks. Logging, structured logging, using ilogger is mandatory. We don't log strings, we log JSON objects with correlation IDs. This allows us to query logs for a specific user session across all microservices. Now, let's talk about summary of the architecture. The theoretical foundation we are building relies on these pillars. 1. Immutability, containers ensure consistency. 2. Abstraction, interfaces ensure flexibility. 3. Isolation, microservices ensure resilience. 4. Observability, telemetry ensures trust. We are not just writing code, we are engineering a distributed nervous system for intelligence. The C# features we use, iHost, background service, channels, interfaces, are the tools that allow us to impose order on the chaotic, resource-intensive nature of AI inference. Turning our attention to basic code example. Imagine a small e-commerce startup. During a flash sale, the website experiences a massive surge in traffic. The product recommendation engine, a critical component for driving sales, suddenly becomes the bottleneck. A single, monolithic service running on a single server cannot handle the load, leading to slow response times and lost revenue. The solution is not just a bigger server, but a smarter architecture. We need to break down our system into smaller, independent services, microservices, that can be deployed, scaled, and managed individually. In this example, we will build a Hello World version of such a system, a simple, product recommendation agent, that is containerized and ready to be deployed as a scalable microservice. We begin by importing necessary namespaces from the ASP.NET Core framework. These using statements are crucial because they bring in the building blocks for our web application. For example, Microsoft.ASP.NET Core Builder is essential for configuring the application's request pipeline. Microsoft.ASP.NET Core MVC provides attributes like HTTP/GET and base classes for controllers, and Microsoft Extensions.Dependency Injection is where we'll register our services for dependency injection. Remember, in a microservices architecture, having a lean set of dependencies helps keep the service focused and reduces the attack surface. Here, we define our product domain model using a C# record. This is a concise way to declare an immutable data structure. Immutability is a powerful concept in cloud-native applications because it simplifies reasoning about state. When a product object is created, its ID, name, category, and price cannot be changed, which helps prevent unexpected side effects, especially in a concurrent or distributed environment. This design choice contributes to a more robust and predictable microservice. We introduced the iProduct repository interface. This is a classic example of the dependency inversion principle, a cornerstone of good software design and particularly vital in microservices. By defining a contract for data access, we decouple the recommendation agent's logic from the specific implementation of how products are stored or retrieved. This means we could easily switch from an in-memory list to a database, SQL, NoSQL, another microservice API, or even a mock service for testing, without altering the agent's core recommendation logic. This flexibility is key for evolving microservices independently. This in-memory product repository provides a concrete, albeit simple, implementation of our iProduct repository interface. In a production environment, this would likely be replaced by a more sophisticated data access layer that interacts with a persistent storage solution like a database. For a Hello World example, an in-memory list is perfect for demonstrating the service's functionality without requiring external infrastructure. Notice the _products list is read-only, reinforcing the idea of controlled data access within this specific repository instance. Here, we implement the getAllProducts async and getById async methods for our in-memory product repository. Notice that both methods return task T, making them asynchronous. Asynchronous programming is crucial for building scalable microservices. It allows the server to handle multiple requests concurrently without blocking threads while waiting for I/O operations, like database queries or external API calls, to complete. Even though our current implementation uses task.fromResult for an in-memory list, designing with async/await from the start prepares the service for real-world, I/O bound operations and ensures good resource utilization. This is our recommendation agent, the heart of our microservice business logic. It's designed to be stateless, meaning it doesn't hold any client-specific data between requests. This is a fundamental cloud-native pattern that enables horizontal scaling. You can run multiple instances of this agent, and any instance can handle any request, simplifying load balancing and increasing resilience. The agent receives an iProduct repository via constructor injection, further demonstrating the power of dependency inversion. This design makes the agent's logic testable in isolation and easily adaptable to different data sources. This getRecommendationAsync method contains the actual recommendation algorithm. For this example, it's a very simple rule: find another product in the same category. In a real-world AI microservice, this is where you'd integrate with a machine learning model, perhaps by calling an inference endpoint or loading a pre-trained model directly. The async/await pattern is used again, ensuring that the operation doesn't block if getById async or getAllProducts async were to perform actual I/O. The simplicity here allows us to focus on the microservice structure rather than complex AI algorithms, but the architecture is ready for that complexity. The recommendation controller acts as the public API endpoint for our microservice. The API controller attribute enables opinionated behaviors for building web APIs, such as automatic HTTP 400 responses for validation errors. Route API/controller automatically maps requests to /API/recommendation. Like the agent, the controller also uses constructor injection to receive an instance of recommendation agent. This separation of concerns, controller handling HTTP, agent handling business logic, repository handling data, is a hallmark of well-structured microservices and promotes maintainability and testability. This getRecommendation method defines our single API endpoint. The HTTP get product ID attribute maps HTTP get requests like /API/recommendation/1 to this method, extracting the product ID from the URL. It's an async method, which is best practice for API endpoints that might perform I/O bound operations, even if the underlying agent is fast. The method checks if a recommendation is found and returns appropriate HTTP status codes, not found, 404, if no recommendation, or OK, 200, with the recommended product as JSON. This adherence to standard HTTP semantics makes our API easy for clients to consume and understand. This program class is the entry point for our ASP.NET Core application. The main method is where the web host is built and configured. WebApplication.createBuilder, args, initializes the host with default settings. Crucially, builder, services.addControllers, registers all MVC controllers, like our recommendation controller, with the dependency injection container. This is the composition route where we declare which services our application needs and how they should be instantiated. This setup is fundamental for ASP.NET Core applications and allows for a clean separation of concerns. Here, we register our custom services, iProduct repository and recommendation agent. We use builder, services.addScoped T-interface, T-implementation, for both. The scoped lifetime means that a new instance of in-memory product repository and recommendation agent will be created once per client request. This is a common and suitable choice for services that might interact with request-specific data, like a database transaction context, or for ensuring that each request gets its own isolated set of dependencies. While our current implementation is stateless, scoped is a safe default and avoids potential issues with shared state across requests in more complex scenarios, which is critical for cloud-native stateless services. Finally, we build the application and configure its HTTP request pipeline. var app equals builder, build, creates the web application instance. App use routing enables the routing middleware, which matches incoming requests to endpoints. App map controllers then maps the controller actions, like our getRecommendation method, to specific routes. The await app run async call starts the web server, making our microservice available to process HTTP requests. The console.writeLine statements are helpful for immediate feedback when running the application locally, guiding the user to the API endpoint. This entire setup is standard for deploying a containerized ASP.NET Core microservice. Thank you for your attention. This lesson is excerpted from Volume 7, Chapter 9 of the C# and AI Masterclass ebook series and from the volume Cloud Native AI and Microservices, Containerizing Agents and Scaling Inference. You can find all the details here, https://github.com/edgarmilvas/C# programming series. The ebook also includes diagrams, advanced examples, and 5 exercises with solutions for every chapter. There are 26 chapters. If printed, it would exceed 600 pages. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.